Shrimp farming in the United States began almost unnoticed during the late 1960s. Worldwide production of farm-raised shrimp grew modestly the first 10 years, then increased rapidly from 30,000 metric tons in 1975 to 560,000 metric tons in 1988. Farm-raised shrimp now constitute about 1/4 of the world's supply, and the industry continues to grow. As with most agricultural crops, shrimp production is based on select species. These species are all members of the genus Penaeus that inhabit brackish and marine waters in tropical to temperate climates. Although many are cultivated to some extent, the great majority of production is attributed to 3 species: Penaeus vannamei, the Pacific white shrimp; Penaeus monodon, the black tiger shrimp; and Penaeus chinensis, the Chinese white shrimp. Each of these species is readily cultured to market size in 4 to 6 months using established procedures, and all receive a high value in the world market. The United States is a relatively small competitor in the international multi-billion-dollar business of shrimp farming. While U.S. producers have immediate access to America's shrimp market, this market, open to international trade, is highly competitive. The potential is there for long-range growth, but it will require efficient and innovative techniques in production and marketing. Shrimp farming should not be considered an easy money business. The hatchery phase, which involves maturation, spawning, hatching, and larval development, requires stable, high salinity conditions, whereas for pond grow-out, estuarine conditions are acceptable. Often, hatchery and pond facilities are located at separate sites in order to meet their respective water quality needs. Water treatment, maturation, spawning, and larval rearing are the major components of a hatchery facility. The water treatment system should provide oceanic quality water with the following characteristics: salinity, 28 to 35 parts per thousand; temperature, 28 to 30 degrees centigrade; turbidity, nil; pH, 7.8 to 8.5; total ammonia and nitrite, less than 1/2 part per million; ionic composition, similar to seawater; and heavy metals and pesticides, nil. Physical facilities for water treatment usually include a seawater pipeline for access to source water, a reservoir for storage and settling of incoming water, a boiler and a corrosion-resistant heat exchanger for temperature control, rapid sand, diatomaceous earth, and/or cartridge filters for mechanical filtration, chlorine, ultraviolet light, or ozone for bacteriological and parasite control. The maturation component of the hatchery is designed to induce adult shrimp to mature and mate, after which they are transferred to a spawning area. The first step in the maturation process is to obtain adult shrimp either by capture from the wild or by culturing captive juveniles to adult size. Broodstock should weigh 40 to 100 grams each. The typical maturation system utilizes an indoor circular black tank, 4 to 8 meters in diameter, that is equipped with dim lighting and a recirculating seawater system. Brood shrimp are stocked at a density of 3 to 10 shrimp per square meter using a 1-to-1 male to female ratio. After a week-long acclimation period, one of the eye stalks of each female is ablated. This process destroys the X organ and sinus gland complex within the eye stalk and stimulates gonadal maturation. The maturation diet should include a complete pelleted feed supplemented with chopped squid, marine worms, or mussels. Feed is offered 3 to 5 times per day, and excess food is removed from the tank daily. Maturation of female shrimp in captivity is easily recognized by the dark lobes of the developing ovaries that are visible through the shell, extending from the back of the head to the tip of the tail. In order for the female to spawn viable eggs, mating must occur. During this process, a sperm packet of spermatophore is transferred from the base of the male's fifth pair of walking legs to the seminal receptacle of the female, located at the base of her third pair of walking legs. Just before spawning, mature mated females are removed from the maturation tank, then placed in a smaller spawning tank that contains well-filtered, mildly aerated water to improve the hatching rate and the recovery of larvae. Females typically release 100,000 to 500,000 eggs per spawn. Eggs hatch 12 to 18 hours after spawning, and the hatching rate generally averages about 50%. Newly hatched larvae, called nauplii, can be separated from unhatched eggs and organic debris by attraction to dim light. Spent females are returned to their respective maturation tanks, where they remature in 1 to 3 weeks. A single female can spawn more than 10 times during her lifespan. The larval rearing component of the hatchery raises newly hatched nauplii to 3-week-old post-larvae that is suitable for pond stocking. As shrimp advance through larval stages, they undergo frequent and dramatic changes in appearance. Each change is called a metamorphosis. Nauplii must change to zoea and then to mysis before final metamorphosis to the post-larval stage. As nauplii, they have undeveloped mouthparts and subsist entirely on yolk. After passing through 5 to 6 substages over the course of 36 hours, nauplii metamorphose to zoea, the first feeding stage. Zoea feed primarily upon phytoplankton such as diatoms and flagellated green algae. Prepared dried feeds are also available as dietary supplements at each larval stage, but are not considered adequate as a complete diet. Because of the limited ability of zoea to seek out food, it is critical that the food density be maintained at adequate levels and kept in suspension by aerating the water column. After about 4 to 5 days as zoea, the mysis stage is reached. The larvae are now capable of more vigorous swimming and can readily feed on newly hatched larvae of Artemia, commonly known as brine shrimp. Mysis pass through 3 substages in the course of 3 to 4 days before metamorphosing to the post-larval stage. Before transfer to ponds, post-larvae are usually held in a larval rearing facility and fed a diet of Artemia larvae and prepared feed for 5 to 8 days beyond metamorphosis. Physical facilities and management methods used for larval rearing vary widely. Typical commercial tanks range in volume from 10 to 100 cubic meters, or about 2,500 to 25,000 gallons. Many hatchery managers prefer sloped or conical bottom larval tanks rather than flat tanks to improve water circulation. Larval rearing techniques are often classified as either intensive or extensive. Using the intensive or Galveston method, desirable species of phytoplankton are cultured in separate tanks, then fed to zoea, maintained at densities of 100 per liter or more in larval rearing tanks. This system requires careful monitoring of larval and food densities in rearing tanks, as well as considerable effort in maintaining algal cultures. The extensive or Japanese method utilizes larval densities of only 30 to 50 per liter and encourages, through fertilization, a phytoplankton bloom directly within the larval rearing tank. Although this system has the advantage of lower investment in labor, it affords less control than the intensive system. Post-larval shrimp can be grown to a marketable size of about 18 to 22 grams in 4 to 6 months at water temperatures greater than 25 degrees centigrade. However, growth is dramatically reduced at temperatures below 25 degrees, and mortality can occur in the range of 10 to 15 degrees. In the southern United States, pond water temperatures are above 25 degrees centigrade for 5 to 8 months only, depending on latitude. In these conditions, it is feasible to produce no more than 1 crop per year. A prerequisite to a successful grow-out operation is selection of an appropriate site, with water quality the primary consideration. The preferred salinity range is 15 to 25 parts per thousand, while an acceptable range is 5 to 40 parts per thousand. It's important to avoid areas subject to abrupt changes in salinity due to rainwater runoff. Do not base salinity evaluations on a single spot check because salinity can vary greatly with rainfall, tide, and season. Try to locate historic records for the area and examine long-term trends. A second major water quality concern is pollution. Agricultural areas receiving heavy applications of pesticides or herbicides should be avoided, as should areas with industrial or sewage pollution. The property selected for ponds should have impermeable soils with a clay content of at least 25%, relatively flat topography, and an elevation of 5 to 20 feet above sea level. Adequate elevation is often the most difficult criterion to fulfill, but it is needed for pond drainage. Other factors to consider are quality of roads, availability of fresh water, electric power, and local infrastructure. The pond itself is simply an earthen basin constructed partly by excavating soils from the bottom and partly by building up the perimeter levees. The water depth should be a minimum of 3 feet in the shallow end and slope to a depth of 5 feet to 6 feet in the deep end. The U.S. Soil Conservation Service offers local assistance in soil analysis and pond design. Although a wide variety of earth-moving equipment can be used to construct ponds, the most precise and efficient is the laser-controlled dirt buggy used routinely for land leveling applications. The water system for the ponds consists of a pump station, a water supply canal or pipeline, inlet and outlet control structures, and a drainage ditch. The size of the drainage culvert used for the outlet control structure of the shrimp pond is designed much larger than that for a typical fish pond. This is necessary to allow complete draining within about 8 hours to facilitate harvest. A concrete harvest box, designed to accept a submersible harvest pump, is generally incorporated into the outlet control structure of the pond. To avoid recycling of wastewater from the ponds, the discharge end of the drainage ditch should be positioned as far as possible from the pump station. The pump station is usually located at the shoreline for lifting water into the supply canal. A variety of pumps is used for this purpose, including axial flow, centrifugal, and submersible. In cases where the depth of water is shallow near the pump station, then dredging or an extended inlet pipeline is required. Provisions must be made in the water supply system for filtration to remove predators such as fish and crabs. Most farms simply install mesh bags or screen panels with 0.4 to 0.5 millimeter mesh to filter water just before it enters the pond. However, in order to minimize damage to native organisms, it may be necessary for new facilities to place screens before the pump or to install self-cleaning screens that return filtered organisms back to the bay. Management systems for commercial grow-out of post-larval shrimp to marketable size represent a continuum from natural ecosystems yielding very low production to highly controlled artificial environments yielding very high production. For ease of discussion, these continuum will be divided into 3 commonly used categories: extensive, semi-extensive, and intensive. Extensive systems are semi-natural systems that utilize little or no artificial feeds. Because shrimp must subsist solely on natural foods within the pond, stocking densities are low, generally less than 20,000 per acre. Consequently, extensive management is considered appropriate only when costs of acquiring land and constructing ponds are low. In the United States, this applies primarily to existing brackish water impoundments that are poorly designed for shrimp culture. Semi-intensive systems utilize moderate stocking densities in the range of 40,000 to 60,000 per acre. Pelleted feeds are offered to supplement natural food organisms, and limited daily water exchange is provided to improve water quality. Production rates generally average about 1,000 pounds per acre. Most of the farms in Latin America and several in the United States are managed semi-intensively. Intensive systems utilize stocking densities in the range of 100,000 to 150,000 per acre. At this density, the shrimp quickly consume the natural food organisms in the pond. As a result, a relatively expensive, nutritionally complete ration must be used. Water quality is maintained through aeration and relatively high rates of water exchange. Production rates of 3,000 to 4,000 pounds per acre are common. Intensive management of shrimp ponds, first practiced in Taiwan, is now practiced worldwide, and it is the most common system in the United States. Here are the procedures for intensive pond management. The pond should be filled with filtered water during April, about 2 weeks before stocking. A combination of inorganic and organic fertilizer is added to the pond to stimulate the phytoplankton and zooplankton populations in the pond. A typical fertilization rate is about 50 pounds of urea, 10 pounds of superphosphate, and 200 pounds of cottonseed meal per acre. However, rates vary depending on the natural fertility of local water and soils. Half this rate should be applied again at weekly intervals to sustain the plankton bloom for at least 2 weeks after stocking. Before purchasing post larvae from an out-of-state hatchery, check regulatory requirements about certification of disease-free post larvae. Some hatcheries may be unable to provide required documents certifying that post larvae are free of non-indigenous viruses, bacteria, and parasites. At stocking, post-larval shrimp are received from the hatchery in oxygenated plastic bags inside styrofoam boxes. Each shipping bag normally contains 10,000 to 20,000 post-larvae, or PLs. It is critical that the PLs be gradually adjusted or acclimated to the water quality in the pond before stocking. This involves opening the bags, providing aeration, and then gradually adding pond water to the shipping water until differences in temperature are less than 2 degrees centigrade, differences in salinity are less than 2 parts per thousand, and differences in pH are less than 1/2 a unit. Many farms combine the shipping bags destined for a single pond into an acclimation tank beside the pond. This tank is aerated, gradually filled with pond water, then drained into the pond. To conform to the number of PLs being stocked, it's important to perform an adequate estimate of PLs in the shipment. This is accomplished by drawing several well-mixed samples of the total volume, counting the live PLs in each sample, then extrapolating these samples to the entire volume. Although a well-fertilized pond with a rich plankton bloom will satisfy the nutritional needs of newly stocked PLs for several days, most intensive farms begin offering small quantities of feed immediately to train the shrimp to eat an artificial diet. Initially, shrimp should be offered a well-balanced 45 to 50% protein fine crumble. As they grow, this changes to a 40% protein coarse crumble and ultimately to a 35 to 40% protein pellet. Feeding the appropriate amount is complicated by the inability to see the shrimp eating, unlike catfish and trout. During the first month, shrimp are fed based on assumed survival and growth rates. The amount of feed offered during this period is small, and the consequences of incorrect assumptions are relatively insignificant. However, at the start of the second month, it is important to adjust daily feeding amounts based on the actual consumption of the shrimp. This can be done by placing about 1% of each feeding amount on each of several feeding trays. These are analogous to dinner plates made out of netting that is loaded with the feed allotment, lowered to the bottom, then checked about 2 hours later to evaluate consumption. If all the feed on each tray is gone, then the feeding rate is increased by 5 to 10%. The addition of feed and fertilizer to the pond greatly increases nutrient levels that stimulate dense populations of bacteria, phytoplankton, and zooplankton. These biological changes lead to dramatic changes in the water chemistry. The environment within a high-density shrimp pond, therefore, can degrade quickly from that of a natural estuarine habitat to that of a sewage treatment pond. During early morning hours, especially in the hot summer months, the high organic load in intensive ponds frequently leads to oxygen shortages, that is, levels less than 3 parts per million. Mechanical aeration is required to sustain suitable levels of dissolved oxygen. A variety of aquaculture aerators are available, including paddle wheels, aspirating jets, and air injection systems. Paddle wheels are the most common aerators. Usually 3 to 4 horsepower of aeration is used per acre of pond area. To evaluate water quality in intensive ponds, it is necessary to routinely monitor several parameters, including temperature, salinity, dissolved oxygen, pH, ammonia, nitrite, and hydrogen sulfide. Many of the parameters are relatively constant in pond systems and can be measured on a weekly basis. However, dissolved oxygen fluctuates erratically and should be checked at least once each day at dawn. Hydrogen sulfide is difficult to measure chemically at the parts per billion level. As an alternative, the pond manager should monitor the pond bottom for accumulation of black sludge with a characteristic rotten egg odor. Most problems with deteriorating water quality can be solved by early detection and use of increased aeration and water exchange. Water exchange rates are usually increased at monthly intervals from 5% in the first month, 10% in the second, 15 to 20% in the third, and 20 to 30% from the fourth until harvest. Seldom is it cost-effective to use chemicals or antibiotics for water treatment in ponds. Shrimp are susceptible to a variety of viral, bacterial, and parasitic diseases, but disease outbreaks are generally a secondary effect of stress associated with poor water quality or nutrition. The most effective method of preventing disease is to manage water quality to prevent stressful episodes such as low dissolved oxygen and to offer appropriate quantities of a well-balanced feed. If sick or dying shrimp are observed in the pond, arrange to send samples to your Extension fish disease specialist for diagnosis. Without an accurate diagnosis, the appropriate treatment method cannot be determined. If ponds are constructed with a sloped bottom and a large drain, they can be harvested by draining the shrimp out with the water. This procedure involves slowly lowering the water level by 50% during the day before the harvest. Then, on harvest day, the remaining 50% is released quickly to drain the pond within about 8 hours. Shrimp generally hold back until the final 6 to 12 inches of water leaves the pond. Then they swim out through the drain pipe. Most American farms minimize harvesting labor by using a submersible pump designed originally for live harvesting of trout. This allows them to lift the live shrimp directly to a dewatering tower, after which they tumble into an ice bath. The shrimp are then conveyed to a scale for weighing in 50-pound lots. Finally, they must be packed between alternating layers of ice to hold their temperature near freezing. Because shrimp have a limited shelf life on ice, arrangements are generally made to have them processed and frozen at a shrimp processing plant. The typical processing procedure involves deheading, grading into size classes, weighing, packing into 5-pound waxed cardboard boxes, then freezing with a thin glaze. Marketing is one of the most overlooked yet essential aspects of shrimp farming. If shrimp are sold as a standard commodity item, they will compete directly with inexpensive imports. The successful farmer will seek innovative niche markets that offer a premium for shrimp produced or packed in a specific way. For example, rather than a 5-pound cardboard box designed for wholesale distribution, the farmer might arrange to have his product packed in a 1-pound transparent vacuum pack for retail distribution. Shrimp farming in the United States is a new business without a track record of success. Although America offers a large and immediate market, international competition is strong. The successful shrimp farmer must combine production and marketing skills while continually taking advantage of technological innovations. The future is bright for those who can produce seafood efficiently because wild-caught supplies are reaching their limit.